Okay, hello. So in this section, we're going to look at evaluating limits algebraically. And we'll start by looking at some basic properties of limits and using those to evaluate limits algebraically. I will give a couple disclaimers. One, I don't do rigorous proof for a lot of these theorems. So if you want something with rigorous proof, this is not the video for you. This is just kind of a brief overview campfire talk that I think is sufficient for Calc 1 students, but not for mathematicians. And also, it's my understanding that you have some idea of limits before viewing this video. So properties of limits. Some functions allow for direct substitution. Basic functions like polynomials, those allow for direct substitutions. Polynomials are defined over the reals. So looking at x approaching any value, you can just directly substitute the limit value into the function. So I'm going to use some standard notation. We'd say the limit as x approaches c of f of x. C is going to be the value that I'm considering x approaching. And then f would be the name for my function. So that's just going to be some standard notation that I'll use. So if I say c, know that I'm talking about the value x is approaching. For polynomials, the limit as x approaches c of f of x just equals f of c. In other words, all you have to do is plug that c value into your function to find the limit. Okay, so that works really well when we have, a constant function, a power of x function. All of those allow for direct substitution. You can see that. So if my function, for example, was f of x equals 3, and I was considering what happens as x approaches 2, well, the limit as x approaches 2 for f of x is just going to be f of 2. And f of 2 in this case is just 3. Because everything, it's the constant function. So this would just be f of 2 or 3. And you can see that similar idea carry out for each one of these. So the limit as x approaches -4 of x is just equal to -4 input. So that's just going to be -4. Inputting -4 in for x, inputting 2 in for x. These are all ones that allow for direct substitution. Evaluating those limits work really nicely. And that gives us some other theorems for limits. For example, we have scalar multiple. I have, in this case, let's say I have the limit as x approaches c of f of x is defined to be capital L, and the limit as x approaches c of g of x is equal to capital K. Assuming those two limits, then we have a theorem that says the limit of a scalar multiple times a function as x approaches c is equal to that scalar multiple times the given function. In other words, you can factor out a scalar from a limit. The sum or difference of two functions' limits is equal to the limit as x approaches c of the sum of the two functions. So in other words, limits hold under addition, limits hold under multiplication, limits hold under division, and limits hold under powers. So we can use those theorems then to evaluate limits. Again, when I'm looking at evaluating a limit, one of the first things I do is I just look at, is the function defined there? If f is defined at c, then it's just f of c, and that's it for most traditional function. There's exceptions for things like piecewise functions and weird cases like that. But for the most part, when we're dealing with limits of polynomials, when we're dealing with limits for polynomials, you just plug in that c value. So for here, I just look at what is f of 2. My function is equal to 4x squared plus 3. So what's f of 2? Well, in that case, that's gonna be 4 times 2 squared plus 3. That's gonna be 4 times 4 plus 3. And that's gonna be 16 plus 3, or 19, right? So we can then say, okay, the limit as x approaches 2 of 4x squared plus 3 is equal to 4 times 4 plus, times 2 squared plus 3, which is equal to 19. So a lot of times a question I get asked is like, how much work do I have to show? And because this isn't a proof rigorous class, you know, you just have to convince me that you understand what's going on. So I would say this stuff that I have highlighted right here, that's sufficient, okay? If you show this work, that's sufficient to demonstrate to me that you have an understanding of the limit, and that's sufficient work. Again, we're not doing proof rigorously here, so if that's a course that you're in, this would not be sufficient. Don't put that, but for my Calc 1 course, this is what I have highlighted is the perfect amount of work that I would expect. And then if you're a visual person, you might be curious, what does the graph look like? And if you were to graph the function f of x equals 4x squared plus 3, you would see it looks like this open parabola, and it's defined when x equals 2, and you can see that point, and of course you see that it equals 19, and so the limit and the function value again agree. It's not a very interesting situation, but you can still talk about the limits even at places where a function's defined. So we call this direct substitution when the limit approaches the value where the function is defined. This property for polynomials where you can take that c and just input it into the function defines the value of the limit. We call that direct substitution. And direct substitution works for polynomial and rational functions that have non-zero in the denominator. So when we're looking at limits of polynomial and rational functions, if I input c to my polynomial in my numerator of my rational function, and I input c into the denominator polynomial, as long as the denominator polynomial does not equal 0, then direct substitution holds for rational functions as well. So if you're dealing with a polynomial function, direct substitution is always possible. If you're dealing with a rational function, it's possible, with the exception being where the function equals 0. When the denominator function equals 0, excuse me. And we'll look at that special case, that there's some special techniques for finding those limits. So let's say we're considering the limit of this rational function. So here I'm looking at the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. So I'm going to look at what is f of 1 in this case. 1 squared plus 1 plus 2 over 1 plus 1. This is going to equal 4 over 2 or 2. So f of 1 is 2. It's defined. The denominator is not equal to 0 when we input that given c value. So we know that the limit exists. Direct substitution works. The limit as x approaches 1 of f of x, or in other words, that above, this is just going to equal 2. So the limit exists and it equals 2. We'd read this as the limit as x approaches 1 of f of x equals 2. So stay tuned and watch the next video, and you can kind of see this theorem applied to radical functions as well.